Hello everyone, this is Dr. Ali, and last session we actually solved this Fibonacci in a recursion manner, and we look at the code, and then I mentioned there are some issues with the recursion functions that actually this Fibonacci is a really perfect example to show what are those issues with recursion. So let's look at the instead of Fibonacci of 4, let's look at the Fibonacci of 5. This is the tree for Fibonacci of 5. This part, I already showed you the tree and we walked through it and we saw different nodes in it. But Fibonacci of 5, we know that it's calculated by Fibonacci of 4 and Fibonacci of 3, right? So this is already we know. And just one thing that I want you guys to notice is look at the occurrence of each one of these Fibonacci's. How many times we call Fibonacci 5? One time. Here, one time. How many times Fibonacci of 4 occurs here? One. But how many times Fibonacci of 3 is called? One, two. How many times Fibonacci of 2? 3 times. Fibonacci of 1, 5 times. Fibonacci of 0, 3 times, right? So this is some of these actually be repeating some of these recursions. So instead of uh, calling Fibonacci of 3 one time, you're calling it 2 times. And when you say Fibonacci of 3, we mean all of these subtrees with it. So look at this subtree and this subtree. So actually I have an example here. I have a diagram here. So Fibonacci of 3 2 times happens, right? This triangle and this triangle. But these are actually extra calculation. We didn't need to run 2 triangles. This one was enough. If we have Fibonacci of 3, we're just using it for this node. Why do we need to calculate it again? Or same for Fibonacci of 2. How many times it happens? 3 times. You see this triangles here? 1 time, 2 times, 3 times. So there are 2 extra calculations here, computations here that we didn't need to do it. So that is exactly the issue with recursion functions, because we do some recalculations here. So look at, that's where exactly dynamic programming come to picture to cover this problem of recursion functions. When there is some recalculation, we just don't want to do it. So as it says here, avoiding the recalculation of a subprogram over and over again. If we have Fibonacci of 1, we don't need to recalculate it here. We don't need to recalculate it here. We're just using it one time and we just calculate it one time and using the result of it for the other occurrence of that. So instead of the O to the, actually this should be 2 to the power of n. Instead of O at 2 to the power of n exponential time complexity, we have O of n plus O of n space. If you don't understand what is these O's means, this is not important for now. This is a time complexity. It means that just for now, consider that showing that how many nodes are here in this Fibonacci. It is 2 to the power of n. For example, here, if n is 4, imagine we have 2 to the power of 4 nodes here, right? 2 to the power of 4 is 16. But if we use dynamic programming, we have only 4 actually nodes here. Those 4s are Fibonacci of 4, Fibonacci of 3, 2, 1, 0. Well, it's 5, but in the time complexity, it doesn't matter. 4 and 5 actually has the same time complexity. But it comes with a catch here that we need to store those Fibonacci's that we calculate. So we don't want to do the calculation. It means that we need to save those calculations that we already did and we use it somewhere else. Okay, so that is the power of the dynamic programming. But to make it a little bit more clear, I have implemented the same code, same Fibonacci with dynamic programming versus recursion. This was the part that we already saw. This is the same for the same problem, but I wrote it in the recursion manner. I mean the dynamic programming manner. Well, dynamic programming also has 2 approach. One is top down, the other one is bottom up. Okay. right now I'm solving it in a top down. We will get into dynamic programming later on, but what I did here, I get rid of these base cases and define a dictionary here. And whenever I calculate a node in this in that tree that we saw together, I store it in this dictionary. And if we want to calculate an Fibonacci for a specific number, we first check this dictionary that whether that number, the Fibonacci for that specific number, exists or not. If it exists, just return its value. You do not need to run this recursion. And if it is not exist in this dictionary, then run this Fibonacci recursion manner. So look at for Fibonacci of 40 in this recursion manner. The value for the Fibonacci 40 is this value, and how much time it took for us to come with this value, 18 seconds. But look at this recursion or this dynamic programming counterpart of it. Same value for the Fibonacci of 40, but look at the time, 0.0004. It's less than 1000x faster than this recursion. This is huge. So if you put here Fibonacci of 50, this program takes forever. It's not coming out. It takes like a minute or something. But for this one, for the dynamic programming, it comes out very fast. So that is the power of why is this dynamic programming is that important, and lots of people go toward dynamic programming and they don't even use recursion, because you see the problem with the recursion for just this Fibonacci. It will take 18 seconds, and if you turn this to Fibonacci of 100, it won't even come out. It takes forever. But for this dynamic programming, it's much faster. So that is the dynamic programming introduction. I will share the both codes in the comment section if you want to try it. And we will see lots of more examples in both recursion and dynamic programming. So that's it for today. Stay tuned for the next problems. And by that, have a great day, everyone.